This is video 48 now in our series concerning electrical circuits. A reminder that the video playlist for all the videos is featured at the website digital-university.org. In this video, we want to introduce the concept of equivalent circuits, specifically on the Thevenin and Norton equivalent circuits. And really probably the best way to do that is just by considering a relatively straightforward example. So here we have a simple circuit with just a battery and a 25 ohm and 100 ohm resistor. Over here a 20 ohm resistor, and we have terminals. We label them A and B. Here's a simple question. If we took a potentiometer and we measured the voltage across A and B, what reading would we get? In other words, what is the open circuit voltage? And we can tell just from looking at it that with the open circuit voltage the way it is, the only current flow is going to be through here, and the voltage drop across the 100 ohm resistor is going to be the same as the voltage drop across terminals A and B. So the open circuit voltage that's just the voltage across the 100 ohm resistor, and I think it was in our very first video where we discussed the voltage division principle when you have resistors in series, and it's pretty simple. The voltage drop across here is equal to the value of that resistor, 100, divided by the total value or the total resistance of this circuit, which is 125, times the voltage source itself, which is 100 volts, and that equals 80 volts. So again, with the circuit the way it is, if we took a potentiometer reading across these terminals, we would get a reading of 80 volts. Now, let's ask ourselves this question. If we put an ammeter across these two terminals A and B, what current reading would we get? Now, when we hook up the ammeter, that's the same thing as if we just drew a line right here and short-circuited the circuit. So to get our to determine the ammeter reading across the terminals here, we would just draw the line here. And now we look at the circuit and we can see, well, it looks like the 100 and the 20 ohm resistors are in parallel to each other. So let's just redraw this. We have the battery, the 25 ohm resistor, the 100 ohm resistor, and then in parallel to that we have the 20 ohm resistor, and what we want to know then is what is the current across this 20 ohm resistor. And again, this is pretty simple to determine. First of all, we can see that here these two are in parallel, so the equivalent resistance here, that's just equal to this times this, 100 times 20, divided by their sum, that's 120. This goes into here 6 times, so that's 100 over 6, or that would be the same as 50 over 3 ohms. So let's just quickly redraw this. So here we have our voltage source, 25 ohm resistor, and this is 50 over 3 ohms. Let's designate this as 75 over 3 ohms, our 25 ohm resistor, and our voltage source of 100 volts. Now, let's look at this and just ask, what would be then the current that would be supplied to this circuit? And of course, that's just simply going to be divided by the total resistance, and here the voltage is 100, and the total resistance is 75 plus 50, that's 125, divided by 3. So, trying to keep things in focus, we can say that the source current is 100 times 3 divided by 125, and that's the same thing as 4/5 times 3, and that comes out to be equal to 2.4 amps. So what that means here, this is 2.4 amps. Going back now, working backwards to this circuit, this 50 over 3, this resistance is the equivalent of these two. So here we have a current coming into here of 2.4 amps. So we have 2.4 amps. But now this current is going to be split between this resistor and this resistor. And we want to know what is the current that goes through this resistor. So let's just make some room here. Remember, I believe it was from our second video, that when you have a current supplying two resistors that are in parallel, if we want to know, say, the amount of current that goes through this resistor, that is equal to, in the numerator, it is the value of the resistor opposite this one divided by their sum times the current that's going into those resistors. So here then, for our simple circuit, we would say that I-20, that will be equal to then the value of this resistor, 100, divided by the sum of these resistors, 120, times the current that's flowing into that combination, that's 2.4 amps, and we work this through and we see that the amount of current going through the 20 ohm resistor here is 2 amps. Okay, now let's go back then to our original circuit. That then means that when we put an ammeter across here, we're going to determine a closed circuit voltage of 2 amps. Okay, now we said the open circuit voltage was 80 volts, and the closed circuit, or the short circuit, is 2 amps. So what that means, as far as what these two terminals see in terms of voltage and current is this. Now we can ask, well, could we replace all of this with a simpler circuit? So let's just imagine, say we had a circuit where the supply voltage was 80 volts and the current going through the circuit was 2 amps. What would be the resistance of that circuit? Of course, that would just simply be and here we have 80 over 2 equals 40 ohms. So what this means is that all of this can be replaced with just this. Here we have a voltage of 80 volts, a voltage source. And here we have a 40 ohm resistor. For this circuit, the open circuit voltage is 80 volts, just like it is here, and the closed circuit current would be 80 divided by 40, 2 amps, just like it is for this circuit. So as far as these terminals A and B are concerned, this simple circuit with a single voltage source and a single resistance is equivalent to this circuit. And what's interesting, as you'll see in the further examples in the future videos, we can use this type of technique when we have a circuit much more complicated than this, and at the end of the circuit, or maybe perhaps internally somewhere in the circuit, there's a pair of terminals A and B, and we want to know, well, with respect to those terminals, what would the equivalent circuit be, where we have just a single voltage source and a combination with that, a single resistance. And this is called the Thevenin equivalent of this circuit here. The resistance of our Thevenin circuit, this is called the Thevenin resistance. This is called the Thevenin voltage. So going back to here, our open circuit voltage, that becomes the Thevenin voltage. The closed circuit like this, that becomes then, it's not called the Thevenin current, it's called the Norton current. We'll explain that in just a minute. But when we determine what this current is, that allows us then to determine the corresponding resistance of our simpler circuit, in other words, the Thevenin resistance. But in practice, as you'll see in the future videos, when we have a more complicated circuit and we want to know what would be the Thevenin resistance of that circuit, usually it's not found in this manner. Here what we did was determine the open circuit voltage and determine the short circuit current, and then just simply divided those two to get the Thevenin resistance. That gives us the correct answer, but in practice, to determine the Thevenin resistance, it's not done that way. What is done is that any current source that you have in your circuit or any voltage source that you have on the circuit gets eliminated. Then when you do that, you ask yourself, what would be the resistance of the circuit across these terminals A and B? Now, if you have a voltage source, the way you eliminate that schematically is just draw a line through it. now there's no more voltage drop. Or if you have a current source, the way you eliminate the current source schematically is you just simply take it out of the circuit altogether. Now there can be no current flowing through here because we have interrupted the circuit. You'll see that in practice in the future videos. For this one, where we had a voltage source, then we just simply draw a line through that. So let's just do that and just redraw it. If we have a line going through here, then what we will have is the 25 ohm resistor in parallel with the 100 ohm resistor. And then coming out here, we have the 20 ohm resistor. And now that we've eliminated the voltage source, we ask ourselves this question. What is the resistance of this circuit as seen across the terminals AB? So what we can do is you can imagine taking a potentiometer and hooking up across these terminals, and that potentiometer puts out a small trickle of current. So imagine a current coming through, and it's going to see this resistor of 20 ohms. Then when it gets to here, it's going to see that the 100 and the 25 is going to get split between them. So it's going to see that parallel combination. So here then, Req is 100 times 25 divided by their sum, that's 125. And that is 20 volts. Excuse me, we're not working with voltage, we're working with ohms. 20 ohms. So, here then we have 20 ohm resistor, a 20 ohm resistor, the total resistance across these terminals, imagine a potentiometer being hooked across here, putting out a small trickle of current, it would see a total resistance of 40 ohms, which is what we determined a few minutes ago. So this is just a simple demonstration that the way that the Thevenin resistance typically is determined is you go back to your original circuit, remove whatever voltage sources or whatever current sources that exist in the circuit, and then across the terminals A and B, ask yourself, what is the resistance of that circuit across these terminals? That would then determine our Thevenin. To get the Thevenin, like this, then what we do is we go back to our original circuit and we ask ourselves, what is the open circuit voltage? That will be this. So that gives us this, and that gives us this. Then we can simply replace this circuit where we have the Thevenin voltage of 80 volts and a Thevenin resistance of 40 ohms. Now, suppose that for some reason when we look at our original circuit and we would like to know, well, suppose that we had more voltage sources and we had current sources scattered throughout, and we wanted to know how can we draw a simpler circuit that just has a single current source in it. Well, for here, we could do that very easily. In video number 22, we talked about source transformations, and we pointed out, or we developed actually, we proved it, that it's a simple thing to show. This circuit is equivalent to having a current source of 2 amps, and now the 40 ohm resistor is in parallel to it. Notice that for the open circuit voltage, that would be 80 volts. So this is the Norton equivalent of this circuit. Now, right from the beginning, if we did not want to know what is the Thevenin resistance of this circuit, but what is the Norton equivalent of it, well, first of all, we have to determine the Thevenin resistance. That stays the same in either case. Then, once we determine the Thevenin resistance, then we want to determine what is the short circuit current. And that will be the current source in the Norton equivalent of the circuit. So that's the introduction to the concept. I hope it was useful. Come back, join us for some more videos. We'll try to consider some more complicated examples and see if we can solve some more problems.